Okay, let us proceed with a more in-depth tabular analysis of the pi experiment, the experiment where we measured the diameter and circumferences of various circular shaped objects. Earlier I did this table over here, and a very crude tabular analysis just involved, just calculating pi by taking the circumference of the diameter and then rounding it off to the correct precision based on the significant digits of the measurements. However, I also did this other method that's not really correct. Remember, we did an average and a standard deviation, and one might be tempted to say, well, that's a tabular result of the average plus or minus the standard deviation, but that's not really a correct way to proceed. And when we do this more formal analysis, I think you'll get an idea why that's the case. You can average data and get a standard deviation. I think it can be justified in many cases, but generally that is not the correct way to do things. So let's do this formal propagated uncertainty for pi. Okay, so I sent that document out and you should have read it. It's the the mathematics behind propagated uncertainties. Now let's read a nice formal definition for the propagation of uncertainty right out of Wikipedia, which is this is a nice definition, this first paragraph. In statistics, propagation of uncertainty, or propagation of error, is the effect of variables' uncertainties, more specifically random errors, on this uncertainty of a function based on them. When the variables are the values of experimental measurements, they have uncertainties due to measurement limitations. For example, instrument precision, which propagate due to the combination of variables in the function. Now, for example, when we're measuring pi, we used either a ruler or a meter stick or a tape measure to measure the circumference and diameter. And notice that each one of those instruments had a smallest increment of 1 millimeter. Now, some folks will use, say, a half a millimeter as the uncertainty, but I'm conservative, and I will say in this experiment, a better choice is probably a millimeter of uncertainty in those measurements. So about 1 millimeter of uncertainty. It's very conservative. Okay, now let's finish our table here. So the first thing we need to calculate are the relative uncertainties in the diameter and circumference. Relative uncertainty in diameter, relative uncertainty in circumference, which is simply the uncertainty, which is 1 millimeter. All the uncertainties here are 1 millimeter for circumference and diameter over the measurement. So we're going to divide 1 by all these numbers over here. So I'm just going to say equals 1 over this number. Okay, so this one's also equal to 1 over it's the circumference. So that's column B. There we go. Now, I can pull these down at the same time so we can save a little time here. There we go. So those are your relative uncertainties, every one of them. And see how it's decreasing as the size of the object gets larger? So in other words, this data would be more trustworthy according to this theory of propagated errors. Now, we need to calculate the relative uncertainty in pi. Now, right here, remember how pi, we're calculating pi. So these errors propagate formally, and if we do the math and do the partial derivatives, we see this formula here. It's kind of like a Pythagorean theorem in error space. We have the square root of the relative uncertainty in d squared plus the relative uncertainty in c squared. Now, why is that? It's because the errors are uncorrelated. If we assume they're uncorrelated, it's kind of like vectors that are orthogonal to each other. They're completely independent of one another. So we can so when you have these, any formula that relates values linearly to the 1 or negative 1 power, even if there's a constant involved, you're always going to get this form here, this relative uncertainty, in kind of like a Pythagorean theorem in error space. So I just say equals the square root of, so we take this squared, relative uncertainty in d squared, plus the relative uncertainty in I squared. That's I4 squared. And then tab out. There we go. So there's your relative uncertainty in pi. Then we're going to pull that down. Now that's all of them, right? Now see how it went down? The relative uncertainty in pi went down with increasing size. Okay, now what's the uncertainty in pi? Well, we just take this relative uncertainty in pi and multiply by each pi, which is this column over here. So equals the relative uncertainty in pi times the pi experimental value. There you go. And once again, you see how our absolute uncertainty in pi goes down. In other words, these measurements should be more trustworthy than these up here. They would be weighted heavier than these up here. Okay, so what's the experimental result? So basically, you just say pi, which is 3.23, this value right here, and plus or minus, we keep one sig fig, 0.08. Now, let's underline that. Okay, so see how that works? Just the result that you got for pi based on measurements, and then plus or minus this uncertainty. Okay, what's the next one? 3.1, actually that rounds off to a 3.20, right? Now, how do I know it's three significant digits? Because the precision of that number, the precision of this number, is determined by where the leading digit is on your uncertainty. So that's 0.07. Round that off. See how that works? And I didn't mean to underline all that. You should always do your underline after you type everything. Excel keeps your last command. Okay, now I'm just going to be lazy and go over here and just grab them like that. I've already done that, so we can save a little time here. I did that earlier. Okay, there we go. Now, then we'll make all these size 9 and Calibri font. There we go. Now, there is one we should mention. Notice this case here. We have an uncertainty in pi of 0.0139 whatever. Now, the leading digit is a 1, so we need to keep the next one. So that would be 3.107 plus 0.014. See how you have 2 digits since the leading digit's a 1? So that's the exception to the rule of one significant figure in your error. And where that significant digit lies determines the precision of how you quote your result. See, that's in the 3rd decimal place, so that's where we keep, that determines the precision of pi that we report. So there's your experimental values. Now, what's the range of those values? Well, the range would be 3.15 to 3.31. Now, does that agree with pi? No, it does not. There is not agreement with our first little. We did not agree. Notice that 3.14 does not fall in this range. Okay, we can do okay, let's do one more. What's the lower bound here? Just subtract 0.07 from 3.20, 3.13. Right? And then what's the upper bound? 3.27. There you go. So that's the range. That agrees. Pi falls in that range. Yes. So I'll just put yes. Okay, there we go. Now let's grab the rest of them just by I'll just go in here and snag them like that because we, just waste time here. Okay, there you go. That's the rest of them. And agreement, yes. Agreement, yes. Agreement, yes again. See how pi falls in there? Agreement, yes. Agreement, yes. Agreement, yes. Agreement, yes. Am I missing one here? I thought there was one that didn't agree. Let me look. Oh, no. Okay. Oh, yes. But I'd missed that one. Look. Oh, yeah, look. Pi is above the upper bound there, so that is a no. See that? No. The pi does not fall in that range. There you go. So there are 2 that don't agree. I'll redden them so we can see. So we point them out. Okay, now, so that basically concludes how to formally propagate the uncertainties into a final result and how you should report data. Now, another good exercise is how would you go about averaging this to get, how would you get a table value based on averaging this? Well, you would have to weight them based on the relative uncertainty. The smaller the relative uncertainty, or the smaller the uncertainty actually, the higher the weight of that value. In other words, you would weight that one more than this one. So I might let you all figure out how to do that for an exercise. In the lab. Okay, have a nice day.